Dear participants, today our first talk will be delivered by Dr. Ila Sharma. Dr. Ila Sharma is Joint Principal Coordinator for this particular our FDP on Advanced Optimization Technique from MNIT Jaipur itself. She has done her PhD degree from Department of ECE IIITDM Jabalpur prior to joining MNIT Jaipur. She has done her MTech degree from JUIT Solan and BE degree from GEC Raipur. Till date, she has 14 journal publication, 13 conference publication, and her expertise area are in the signal processing, multi-rate filter design, and multi-rate techniques application in communication system and cognitive radio. So I request Dr. Ila to start the session. Over to you, ma'am.
Thank you, sir. Thank you, sir, for this warm welcome speech to me. I'm very thankful to you for providing this opportunity. So, participants, welcome to this AOT 2025, and our today's talk is filter design using optimization. So till now we have covered so many optimization technique like PSO, ant colony, and many other classical techniques as well as the recent one. So we'll do or we'll apply those techniques, or we'll see in our lecture how these techniques are being applied to design any filter. But before proceeding to the optimization of filter, firstly we have to know about the filters. Okay, I'm not covering the entire filter thing, but we have to have that base with in our mind that what are the requirement where we have to apply optimization and why we are doing so. So first of all, what is filter? In signal processing, filter is a system that performs mathematical operations on a sample discrete time signal to reduce or enhance certain aspects of the signal. So this is a definition one. But whenever we ask about the filter, a simple thought come in our mind, that is a filter is a thing that is useful for altering the some part of frequencies and passing some parts of frequency. Isn't it? Some part of frequencies are being restricted and some part of the frequencies are being passed, and accordingly we have one figure in our mind where we have seen the low pass, high pass, band pass, and band stop filter. So this is the very layman or a bird eye view of a filter which comes in our mind. But when we start to design it, like it is applying to any of the domain, like you know that filter is a very important component, and if you see any domain of the engineering, whether it is electronics, where it is electrical, mechanical, whatever it may be. So if we are dealing with any kind of input meaning it can be of naturally generated input, it can be of lab generated input, and this input to any devices, any system, whatever it may be. So whenever we give any input and want to know about the system responses, about the system output or a transfer functions or what actually the system is doing, so we have to analyze and we have to pass it through a filter or kind of component which is designed for a specific use. For example, if we are dealing with any frequencies which are low in a nature, Like we have some signals meaning, let's suppose we have some sinusoidal signal or some composite signal or any signal, but they are having low frequency. So what we need to have, we have to figure it out that how it can be amplified smoothly so that it can be given to input to the another connected device. So definitely we have to use some low noise amplifier. So what it is doing there, it is removing the noise component from the signal and then amplifying it. So the main task is that whatever the required part of portion of the signal is there, we are focusing on any signal or any output. So that need to be reconstructed or extracted or filtered. So everywhere whenever we talk about signals, we need to have that filter to define its properties or accurately extracting the useful information from the filter. Then again, our so many classifications of filters are there. Like if we are dealing with the analog signal, then we will be having the analog filters for extracting those information. And when we are having digital sequences, digital signal, then we need to have that digital filters. So this is one classical classification of the filter. But in today's class, I will be focusing on a digital filter only because otherwise it will be very vast, and you know that there is a comparison, there is a pros and cons of this analog and digital filters. So I will be focusing on a digital filter, and from the digital filter point of view, whenever we compute means digital filter, meaning we will be dealing with the digital sequences, digital signals, like in the input of the system and the output of the system, both will be the digital sequences or the digital signal. Now again, we need to know about the classifications, further classifications, how it will be designed. So the very first classification of these filters are based on the calculation of impulse responses. Now, what is this impulse response? You know, whenever we have any system, okay, there is a system like here in my slide, you can observe this square box is there where FIR and IIR written. Let's suppose this is your X box. You don't know what it is doing. What is the characteristics of this filter, whether it will amplify the signal, whether it will be degenerating the signal, whether it will be acted as a adder here. We don't know about that. It is X box, let's suppose. And we need to compute the output of it, meaning to what, whatever we give input to that, we want to calculate the response of that system. And whenever we compute the response, we simply define our transfer function, that is output by input. Got my point? What is transfer function? That is represented by h of omega, h of n, and that will be output upon input. And whenever in input we apply impulse signal and then we compute the output of the system, that is called impulse response of the system. Its simple definition is that any system, when we compute the output and if we apply the impulse sequences there and then we compute output of it, that is called impulse response of the system. Similarly, we have step responses and ramp responses because these are the elementary sequences or elementary signal. One more thing I want to clear out, as we are discussing this digital filter, that's why I'm using this sequence word. Otherwise, I have told you about this samples, or otherwise I have told you about the analog signals also. So sequences means those sample value. In digital signal, we deal with the discrete signals, and those discrete signals are what? That is giving the samples value. Like here in our figure 1, in the output side, you can observe these are the sample points. This can be increased, this can be decreased. This is a discrete sample signal. It is not continuous. I hope you understand the difference between this analog and the digital signal. Isn't it? You know about this? The difference between the analog and the digital signal? Okay, moving ahead. So we discussed the impulse response system, and based on the length of this impulse response. The filters are again classified as finite impulse response filter and infinite impulse response filter. Finite impulse response, there will be finite duration of these sequences. Like here in the figure, we will be having some sample points that can be counted off, that can be calculated, that have the finite number. Whereas in IIR, it is the infinite series of impulse responses that has been taken or output has been computed when we have infinite series of impulses as a input. So this is a classification of FIR and IIR filter. I hope you got this. Okay. Then again, this basic picture, this basic 4 types which we have in our mind, this you can observe, these are ideal low pass, ideal high pass, ideal band pass, and band stop. And this 4 type of filters can be designed by using FIR filters, can be designed using IIR filter. Okay. But you can observe here, these are ideal ones. The flat magnitude response, if you observe the very first one, that is representing your low pass, the subscript is also indicating that H of LP, LP indicating low pass, H of HP, high pass, then band pass and band stop. And these all are analyzed in frequency domain. Basically, the functions has been computed by using Fourier transform here. Fine. This was the observation. So there are some observations. As the impulse response corresponding to each of this ideal filter is non-causal and of infinite length, these filters are not realizable. First observation. Second, the magnitude response specification of a digital filter in passband and in stop band are given with acceptable tolerance. There is some specific value given to it. And in addition to transition band, that is specified between the passband and the stop band. You can observe what we are discussing, that I think, can you see my pointer? Yes, it is showing. So you can observe we have this pass band region that is having value of 1 constant, fine. And we have this stop band here, which is having this value 0. And the transition band, which we are talking about, that is this one. This is very abrupt transition from this 1 value to 0 value. So this is our ideal filter. And that is replicated to all, this high pass as well as band pass, then band stop. But very interesting, when we design this filter, so the response come out like this. Okay, this is the generated low pass filter, you can see. So clearly observing the difference between this ideal and the generated one, you can observe in a pass band, we don't have that smooth response that was needed and that was there in your ideal low pass filter response. You can observe there is this simply fluctuation, you can say, or ripples, you can say. Those values are from 1 plus del P to 1 minus del P. And del P is your passband ripple. We will be discussing how it is calculated in the later upcoming slide. But just observe this figure. It is not smooth, it is not constant, and it is fluctuating or having this ripples in this lower and upper boundary of 1 plus del P and 1 minus del P. So till the passband, it is behaving like this. And in the stop band again, here, this is not flat 0. Again, it is having some ripples denoted as del S, stop band ripple. And this transition band, you can observe, this transition band is not abrupt transition, it is slanted. So these are the differences of ideal filter to a design filter. And here, why we are doing optimization, answers come. You can clearly see this observation. If we employ any of the filter, like whether it is required a low pass, whether it is required a band pass, you need to have that design filter should be acting as the ideal one. Then only your required aim will be achieved. Like you have to filter out some spectrum that is spreaded, like you have a continuously signal spreaded over from 0 to, let's suppose, 2 pi, but you need to have spectrum in between this, like you want to have from pi to 2 pi. So you are actually extracting those sample signal from this continuous spreaded signal, and for that you need to have good filter, like the ideal one. Then only you can extract those. And if you can observe this design filter that is having ripple all over to pass band and the stop band, so it will not accurately reconstruct the signal or accurately extract the information. So what we want to have, we want to have this ripple to be zeros, whether it is in a pass band, whether it is in a stop band. Then only it will be behaving nearest to the ideal one. So ideally what we want to have, we want to have this del P should be 0 or to a minimum value. Similarly, in a stop band, we again want this ripples not to be there. And talking about this transition band, it should be sharp transition, not the slanted one. So this is how we create some kind of objective functions that involves all these operations in pass band, in a stop band, and then we formulate this objective function or a cost function according to our need. And after that, any optimization technique, whether it is a PSO, ABC, that can be employed to make it or to achieve those minimum or maximum value according to our cost function. So we will learn in upcoming slide how these cost functions are being made. But before then that, we need to have a look towards this all the parameters, because we will be directly imposing those parameters while making the objective function. So you should know about the parameters. So I already explained you about this, that we have this magnitude response that is from 0 to omega p, and magnitude response is this mod of g e raised to the power j omega, that is giving your magnitude response or amplitude response, you can say. And we are taking responses in a frequency domain. Fourier transform has been taken, so we will be having our magnitude response as well as our phase response. So talking about this magnitude response, so in a pass band it is spreaded over from 0 to omega p, and it is varying in between this value 1 minus delta p to 1 plus delta p, and this is the frequency where omega is less than equal to omega p, defining this all would be in your pass band region. And in the stop band, defined by this omega value, would be in between omega s to the pi, and with the ripples of del s, so this magnitude function will be like this value in this range. It is how we mathematically define our responses from the spectrum. And again, this omega p, omega s, the subscript value, it is giving information about your passband edge frequency, stop band edge frequency. Then you have peak passband ripple, peak stop band ripple. So one more observation, since our magnitude response is a periodic function of omega, and this magnitude response of a real coefficient of digital filter is an even function of omega, that is spread over from axis to this side to this side. I hope you understand the even function, odd function, because it is very basic. And because of this property, the filter specifications are only given for the frequency range from 0 to pi. So we have considered this 0 to pi. And one more magnitude specifications are given, that is in normalized form. Many of you have also observed some similar kind of responses that is given in a normalized form. So for timing constraint, I have not taken any other representation of this, the normalized form. A normalized form is very simple. Whenever we take the maximum value and we divide it with the accesses value, we normalize the term. Like if we have this pi value and maximum will be the pi, so it will be like from 0 to 1, depending on the whatever the maximum value you have of that function. So the maximum value is divided to all the ranges, all the access value, and that is how it is normalized. So if you have worked in this domain, or if you have worked with the signals or the communication or in MATLAB, so you know about this normalized form. Also, this functions are given, or this is are calculated at dB, like peak passband ripple. These are the standard formula. Okay. So, as we have seen these two figures, one was the ideal one and another was this design one. So basically our consideration is that the passband should be as flat as smooth without ripple. Stop band should be as flat as possible, value should be 0, and then we should have this sharp transition in a transition band. So optimal frequency response, we can conclude that may be having less passband error and stop band error with least possible order. Least possible order, what does it mean? You understand about this order and the length? Okay, I will tell you. If there is any filter when we design that is having main component like adders, multipliers, and a delay line. Like if you can recall the Z transform of any filter, or if you have gone through the transfer functions of FIR and IIR, we will be having that in slide also. This one, like this H of Z, this is a simple transfer function and representing for this IIR digital filter. So you can observe this is constructed with this plus signs. You can observe that are adders, like P0 plus P1 into Z inverse. So this into will be your multiplier. Okay, and the delay line that is being collected to them. So if you realize this filter, so you need to have this 2 or 3 basic components, adders and multipliers, when you realize this in a hardware. Okay, and complexity of designing this filter or realization of this filter directly depends on the order of the filter. Like you have heard about this order, second order filter, third order filter, fourth order filter. What are these? So as you are increasing the order, complexities are also increased because that are directly connected to your increasing of your adders, increasing of your multipliers. But as you increase the order, you get the responses more accurately, more nearest to the ideal one. In many of the techniques, it has observed higher the order, higher the performance, but higher the complexity. So we want to make, or we want to have low order filter, means why to increase complexity, why to increase the resources, because multiple numbers of adders, multiple numbers of multipliers will creating delay, will creating more resources, more memory, more area. So if it is possible to reach to a desired aim with less number of order possible, with less passband error and stop band error, then we need to choose that. So optimal frequency response should be such as that should provide this first objective of our. Second would be filter performance should not degrade upon quantization and truncation of a filter tap coefficient. This is directly related to your designing part, your realizing part, this filter in a hardware, that whenever we realize that thing, no, the continuous coefficients are being converted to the quantization coefficient, quantized coefficient you can say. If you have observed, the coefficients values are generally in a digital form, and after so many values to this coefficients, that will be having some decimal points, and these decimal points are up to the range of 10 raised to the power 12, 13, 14 and 15, and that are also differed. So it is a standard method that it is realized when hardware, like in Verilog or Cadence, whatever it may be. So you have to change your continuous coefficient to the quantized one. And quantization is simply done to rounding off or truncating this sequences, this coefficients value. So we will also discuss this part, but firstly we will focusing on optimization of this filter, which is designed in such a way that it should fulfill this less passband error, less stopband error, and it should follow the property nearest to the ideal filter. Let's stick to that. So now our objective is clear that we have to design that filter. Now the important question comes, the selection of the filter type. As I told you that based on the responses of the filter, impulse responses of the filter, you have two kinds, IIR and FIR. And you can design any of these 4-5 filter, low pass, high pass, band pass, from these two, meaning IIR filter, low pass IIR filter, high pass IIR filter, low pass FIR filter, high pass FIR filter. So this can be designed in any of the way, but there is a pros and cons. The very important thing is stability. Second, linearity. Stability meaning the function should be stable. The transfer function should be stable. So you can observe in a IIR filter, we have both numerator as well as denominator coefficients. Whereas when we talk about the FIR filter, we have only numerator part. So because of this feedback term, because of this denominator part, because of this poles, the IIR filter are not stable. And it is always having non-linear phase. This is the drawback or cons of your IIR filter. In the other part, when we compared with this FIR one, FIR will always give a linear phase. That is the property of it. And also it's stable. It can be stable. But when we see the complexity wise, the requirement of the filter order, like you know that just I told you, it is defining the filter order, and based on the filter order, higher the order, higher the performance, you know, right? But if a specific application is there and the requirement are specified, and it is observed, many of the authors has been written that thing in a book, that to achieve a same objective, IIR filter requires less number of order, whereas the FIR requires higher number of order. Means to achieve a same task, IIR required less order, like it can be fulfilled by 10th order or the 11th order, whereas in the case of FIR, to design the same thing, to achieve the same aim, that will be 20 or 30. This is one example I am telling you. So this is the basic difference, and you know about this complexity, resources, everything. So that is why this is pros and cons, and depending on the requirement, the person can choose that particular filter can be made with the IIR or the FIR, right? So selection of the filter type totally depends on the application's requirement, because if we are using IIR filter, so we need to provide some aid to make it stable. We need to provide some aid to make the phase of the system linear. So generally, combining with the all-pass filter, the IIR filters are mostly make stable and a phase nullifier. You know all-pass filter, so that is in combination with IIR filter that is being used as a phase nullifier, and then it can be used or it can act as a stable and linear IIR filter. So again, this is the choice of the engineer, what he choose, and there is a trade-off in between them. So objective of this digital filter is that to determine the realizable transfer function. Again, it should be stable, it should be linear, it should be accurate, it should have low pass band error, low stop band error, right? It should not have any delay. So these are our requirements. So for digital FIR filter, here I will consider in today's lecture the designing of FIR filter for simplicity, because in FIR we need to realize or we need to have only zeros or less number of coefficient as compared to IR. So I will discussing this FIR digital filter more. So transfer function of this FIR digital filter can be given by this function h of z, where small h of n, okay, you can see my cursor, small h of n. This is representing our filter coefficients. This capital N is our order of a filter. You can observe it has started from 0. So length will be n plus 1. Many people get confused, means in my class some of the students ask, ma'am, why I always get confused with the length of the filter and order of the filter, because the classification of these filters, again the FIR one will be type 1, type 2, type 3 and type 4 that we are going to see. So it is very simple. If it is starting from 0, so definitely the coefficients will be from n plus 1. So the length of this sequence will be n plus 1. That is your length of the filter also. So order is n and the length will be n plus 1. And for reduced computational complexity, this n should be as small as possible. You know that we are designing this FIR digital filter, so our aim is one more addition, that this capital N value should be as small as possible, means with the minimum order we should achieve to the desired characteristics of our filter. So till now, how these FIR filters are being designed, there are two distinguished approaches. The conventional one, that is translation of this analog filter to the digital one, then suitable prototype analog filter, that is any Butterworth, Chebyshev or any approximations are being taken. Have you heard about this Butterworth filter, Chebyshev filter? This approximation, they have a very standard transfer functions. You may have solved this numericals also in your digital signal processing, or because in our BTech, in our MTech, in BTech, there is a dedicated course for this signal system, and then we have a digital signal processing where you have learned about this filter design. So these are very classical techniques or the conventional approaches. And after then that, you have heard about this windowing technique. Windowing is also very tricky, because we have a different type of window functions, and according to that, we can fetch our spectrum. You heard about this Blackman window, Kaiser window. There are so many windows, they have their window function. And these are directly multiplied with our input signal or whatever the spectrum are there, that is continuously spreaded over all the domain. And you have that window function that is restricted with some limit, like it is having some length, and that is being multiplied to your spreaded signal. And the simple multiplication, that part of the spectrum is finally multiplied output. Like if you can observe that if you employ any rectangular window is very basic type, that let's suppose you have a rectangular window that is spreaded from 0 to 4. Okay, and you have a continuous long sequences from minus 100 to 100, let's suppose. So if you multiply your sequence with this window, rectangular window, so what will happen? The output will be multiplication version of your rectangular window, and final output will be spread from 0 to 2 only, and rest of the sequence will be nullified. So this is called windowing. So based on the different window functions, like they have different shapes that are being employed with that are being multiplied with the sequences, and output are being filtered out. This was the conventional approach. And then we have optimization based approach, where formulation of the design problem or the objective functions are there, and the computer aided design methods are being used to design the filter. And after that, we have a different nature inspired and the evolutionary technique that are being employed. in the formulated objective function and the parameter of optimizations are constructed. I hope till now you have cleared the concept about this filter types, and what is our requirement to design a good filter. So in this slide, I am showing that if you want to design some filter, so you cannot directly design the filter. You should know the further types of this FIR filter. I have write this linear phase FIR filter here because FIR filters are giving always linear phase. Okay. And further classification of this, you can observe this is based on the symmetry, even and odd. If it is even symmetric, if it is odd symmetric, and then again based on the filter order type. The filter order can be even, the filter order can be odd. Even and odd meaning here filter order. Can anybody say if my filter order is even, what does it mean? What would be the values of this? Can anyone tell me what is even order? Any value in between 0 to 10. Fine. Even meaning, let's suppose from 0 to 10. How many even number of order can be possible? That can be 2, 4, 6, 8, 10. And odd orders will be 3, 5, 7, 9. And symmetry meaning, if you know the sequences, if it is even symmetric meaning, left hand side and the right hand side sequences will be same, and there is a no sequence in the 0th term, whereas in the odd there will be one sample at the 0. You have to recall some part of the signal processing so that we can distinguish the different type of signal. So based on the symmetric and based on the filter order, again some of the filters can be designed, some of the filters cannot be designed. For example, in this given table, you can observe the first type filter, type 1. This is called type 1 FIR filter, type 2, type 3, type 4 FIR filter. So you can observe in a type 1, you can design all kind of filter. But if you have type 2 FIR filter, the second row, the second number, that is, if symmetry is even and filter order is odd, then you can only design low pass and band pass filter from that. So type 2 filters is always giving low pass and band pass, whereas in a type 3, where we have odd symmetric and even order filter, then we can design only band pass filter, whereas for type 4 filter, we can design only high pass and band pass. So there is a certain specifications mentioned. These are the standard table. Okay, and this is I have taken from one of the very renowned book, that is the S.K. Mitra, from the chapter 5. I have taken this table. I have not mentioned here, but in reference I think I have given that thing. So this is very standard table. The simple table I just show you. This is the standard table. Above that table, h of omega is specified. This is your magnitude response. Okay, and some of the detailed informations are also mentioned here. What will be the phase response, how the magnitude response will be differ. So all things are specified in this table. That's why I explained the simple table first, so that you can go through this, the second table, that is the standard tables given in the book. So here the magnitude response which we are talking about, that is having this exponential components, then we have this, and then we have this AK terms that is representing the different coefficients value, and that is coded with this cos term. So this is your magnitude response. See why we are reading this, because this is very important. We need to know about the characteristics of your magnitude response, because while formulating the objective function, we will be considering the magnitude responses all over. So now the question comes, how this objective function is being formulated. Again, just recall the ideal low pass filter. I am taking the example of low pass for easiness. You can take any kind of filter for designing. But here I have taken the low pass filter for simplicity. So as I told you, in a low pass, we have an ideal filters response that should be, the magnitude response should be 1 or a constant value all over the passband region, and the value should be 0 in a stop band. Fine. So just observe this function here that is being formulated. F of x, minimum of this mod, that is h of e raised to the power j omega, subscript is I representing the ideal filter, minus magnitude response of this h of e raised to the power j omega, in subscript it is d, that is the design filter. So I'm calculating the error value or the difference value of ideal magnitude response and the design magnitude response. You can observe that ideally it should be 1, it should be constant value, but when we design it, you know there is a fluctuations, like you recall that ripples are there. So definitely its value is not 1, it is above than that, differing that. Let's suppose whatever filter you have designed, you are designed by any of the approach, the classical, the windowing, whatever it may be. So it is not giving the constant value throughout the passband region. So it is giving fluctuation. So its value would be like 0.98, 0.96, 0.97. So basically it is not 1 another than that. So we are computing this error value, and we are computing this from all the passband region. So ideally we are computing 1 minus all the calculated design filters magnitude response, and we want to minimize it as minimum it can possible. Why we are doing so? What will happen if we minimize this? Can anybody tell me in a chat box what will happen if we are comparing our ideal filters response to the design filters response? So what will happen if we are getting the minimum value, minimum error value? Anyone? Okay. Okay, Ajay, I'm just explaining what will happen. If you have this magnitude response, okay, that is spreaded from 0 to omega p, right? This filter response from 0 to omega p. So this value, let's assume it is constant value of 1, right? So this is our ideal filter. But when we design a filter with any of the approaches, what happens? It is having this kind of fluctuation and this kind of fluctuation. This is your omega p. So instead of having this one value, we are having this fluctuation. And when we compute from this 0 to omega p, there is a difference. And we want to minimize this difference, because if this difference is minimized, meaning if it is having one value at this sample point, it is having one value at this sample point, the one value is 1. And here we have 0.997, then 0.996, then 0.998, 0.9 something. This is just assumptions. There is a fluctuation in the value. So error will be computing like 1 minus 0.997. So it will be like 0.001, 0.01, 0.02, 0.17. These values can be differing. But when we minimize it, this is the division of them, this is the subtraction of them. Minimum meaning these are becoming nearest to one value. If one value is 0.98, the difference is 1 minus 0.98. What will be the difference? Anyone? 0.02. Let's suppose I have designed one technique which is having magnitude response of this filter as 0.7. What will be the difference? 0.3. So I have designed a filter whose magnitude response is 0.98. Okay. And let's suppose another student has designed a filter whose response is 0.7. So error is 0.3. So what is the minimum error? 0.3 is minimum or 0.02 is minimum? Which one is minimum? Anybody can tell me? 0.02, right, Shefali? Thank you. So error is minimum, meaning our design filter is becoming more nearest to the ideal filter, isn't it? This becomes comparatively to this ideal filter. That is our requirement, that is our aim. I hope I am clear now why we are taking the minimum of this error. So we are taking those values of impulse responses or the samples of the signal that is nearest to the one value, nearest to the ideal filter value. So you have to design a filter in such a way that is giving the minimum error when compared with the ideal one, and that is our design problem. That's why this kind of objective function is formulated. See, if you want to optimize, if you want to apply this optimization algorithm in any of the field, you have to first construct your objective function, your cost function. This cost functions can be minimum of something or maximum of something. I think you have already gone through this linear optimization thing. If I have a function x plus 2x is equal to 1. So what we are doing, we are taking this cost function that is the minima of this, meaning minimum value of fx, that we need to find those x value by putting which to that a function can achieve this one value. Similarly, we have to identify a problem, maximization of function of something. So this is how we try to make an objective function that can minimize the function, that can maximize the function depending on which parameter you want to optimize and what is your field of optimization, means what you want to do there. Your cost function defines the identified problem solution. So similarly, in my case, when I want to design a good filter, I have formulated this objective function like this. This is the simplest objective function. In upcoming slide, we will be seeing some constraint, like we will be defining. This is related to only the magnitude responses, but there we can be dealing with the passband ripple value, the stop band ripple. These constraints can be employed there. I hope now it is clear. So this is one cost function that I have kept in my mind. I formulated that, and now we will see quickly how the optimization can help me here to get this function minimized. Till now, you have already read about this optimizations. For simplicity, I have taken the PSO here. I am skipping this introduction part of PSO because we have already studied. However, I have implemented this with the PSO, DE, Cuckoo, everything. And I have also taken some of the graphs here, which I will show you. But firstly, I want to tell you how this optimization can employ here. So you know about this PSO that we have this velocity updation and the position updation. See, this is the design steps. I make it full screen. So our objective function is that which we have constructed. I have taken that thing in objective functions. And firstly, we need to give or we need to initialize the parameters that are being used in every standard design problem. We need to initialize the different parameters. So here passband frequency, stopband frequency, ripples, filter order, then controlling parameter and the tolerance value of the filter, these all are specified. And as far of our optimization using this PSO, so we need to set this control parameters W, C1 and C2, then phi1 and phi2, and then again we have to specify maximum number of iterations, because either the stopping criteria should be met or the function should be running till the maximum number of iterations. So we need to specify these iterations can be of 40, 50, 100, whatever the value you want to take. Depending on the convergence of your algorithm, the iteration can be further modified. So initially I will suggest start with the less iteration and then try to increase and then find when your conversion is happening, then you can set the final iteration value. So based on this initial parameter initialization, then we have to create an population partition matrix. The positions and the velocity, then dimension need to be specified, and then we have to calculate the fitness function, that the objective function which we have formulated. One point I have to clarify here is that here my parameter of optimization is currently, that is a filter coefficients. Okay, means each of the samples I'm optimizing in such a way, I'm taking initial parameters as this coefficients, and I will optimize in such a way that in passband those values should be 1, in stop band those values should be 0, and when we compare with the ideal one, the error should be minimum as possible. Till now, are you with me? Did you get it what I explained for this PSO? Anyone? My parameter of optimization is here filter coefficients, and I'm looking for those coefficients through which I can make my objective function working in such a way that it will give the minimum value. So I have a set of parameters. Let's suppose I have specified my filter order to be 10. So definitely how many coefficients will be there? There will be 11 coefficients. And if I am taking the symmetric case, so how many coefficients will be there? 6 or 7? Okay, let's, for simplicity, I tell you, if I'm taking the n order 10, so length will be 11. So I will be optimizing this 6 number of coefficients. Fine. So my initially the matrix, what I will make with the lower limit and the upper limit. So let's suppose my population size is 50. So meaning to what? I have that matrix from 1 to 50. So each row will be having 6 coefficients. So I have this coefficient matrix from 1 to 50. And my task is that every time first coefficient set will be there, given there. The magnitude response will be calculated. The magnitude response will be computed. The error will be calculated in another matrix, the p-best value. Fine. The second coefficients will be taken out. The magnitude response is computed. Again, objective function is compared. The compared error value will be given to another matrix, the second p-best. Then again and then again, it will iterate. How many type of, let's suppose I have specified 10 number of iterations. So it will be done 10 times. So every time the p-best value will be identified, and at the end, I will be having that matrix that is having that p-best value, and among that from p-best values, whatever value is having minimum error, like we have a error matrix in 10 number of components, the 10 number of rows, whatever is having the minimum value, that will be my g-best. So that will be my minimum error cost function, and corresponding to those coefficients will be my ideal coefficients or my optimized coefficients. So that is written in this algorithm steps. Am I clear to you all what I am trying to do using this PSO? Taking my parameter of optimization as a filter coefficients, I have made one objective function, and now I am calculating the magnitude response, comparing again and again, and finding this optimized coefficient from which I can get the minimum objective function value. That was the main aim of this. So I have employed this PSO here. For that, compute the new particle position, then velocity, then again calculate fitness value, then check if present value is less than the previous value. If yes, assign that will be the updated one. Otherwise, we'll go back to the step number 5. And then we will find again and again, we will be having some error matrix. Then again, we will be checking fitness value for our global best one. Then we will compare which one is less than the current one is less than the previous one, or the which one is having the minimum value, that will be pronounced as the G best. And then we will be checking the stopping criteria, whether it is achieved to the minimum value or it is achieved to the maximum number of iteration. Till then our program will run and we will get the optimal values of this. This is a simple flow chart I have made, so you can go through that quickly. Whatever I have explained, that is written here. And once I get this optimal value, either the stopping criteria is met or the tolerance value, let's suppose error is specified as 0.001, that is our tolerance value. Below than that, no error will be computed. So automatically it will be stopped. So those coefficients will be your optimum one. The corresponding fitness is giving minimum value. So this was the applied PSO in a filter design. This was a low pass filter design. You can observe the first one is with the PSO and ABC hybrid of that. Then this figure is showing the filter magnitude response when PSO is employed. Then the quantum PSO, ABC, and cuckoo search. Actually, this result so I got, and that is published in one of the papers. So I have taken directly. I want to show you that there is a difference of each optimization algorithm while designing the same problem. Means objective functions was same, okay, and different optimization algorithms are experimented on that, and accordingly this magnitude response are being generated. Each of this magnitude response is representing the optimized coefficients values based magnitude response. The high pass, similar to fashion of this low pass, high pass, band stop, these can be designed. And you can observe the differences also. So beauty of optimization algorithm is that we have to achieve to the minima value or a maxima value of any cost function. But based on the algorithm steps of this optimization algorithm, including the complexity, the processing time, every optimization results give the different set of values. So these are some of the results. Okay. And once you computed your magnitude response, then for verification whether whatever you have computed that is giving some significant results, particularly in your filter design, these are some parameters about calculating. Through that we can compare, like in my case I have shown you the figures where the magnitude response is generated from 5 different optimization algorithms. So I compared on this ground, like passband error computed in each of the case, then stop band error, attenuation, maximum passband ripple, stop band ripple. So these are the matrices. These are my parameters I computed, and I compared each of the algorithm on this ground. Because if you have designed something, you need to compare, right? Whether it is giving some useful contribution or not. So these are the standard parameters for filter. And you can recall I told you about this quantization. So I show this slide for a specific purpose, that whenever we quantize our continuous coefficient like rounding off or truncating, so whenever we limit those responses, like the coefficient value is 0.0012 up to 10 to the power 12. Now you want to limit into a desired number of decimal points. Like this is called word length. Like you have 0.0020 till 10 to the power 12. So you will be having word length of your 12. And similarly, you can have word length of 14, word length of 16, word length of 8. So you are restricting your coefficients value to the different length. So what is the effect of doing that? Okay. If you have word length of 16, you need to have 16-bit register to store that value in your hardware, the memory thing. So you have to choice which word length value, which means how you gonna limit your continuous coefficient, because ultimately you have to realize that thing in hardware, no? So you need to do that. So this is the effect of different word length on the design filter. So I have also referred this thing in my reference section. And at the end, the application, I think we have already discussed about this filter. Like this the filter can be employed in image image processing, where you can use this for compression, you can use for this noise removing. Similarly in a video, similarly in a audio, you can use this for compression as well as removal of noise, or for subband decomposition. You can use this filter in wireless communication also for getting the spectrum, a particular spectrum fetching out. You can use this in signal processing. This is all defined with it, like signal alteration, whether you are using amplification, whether you are removing the no noise, or you are converting the signal to the higher value. High pass filters can be used. And in medical signal processing, to analyze the signal in a specific thing, like you have EMG, you have EEG, you have ECG, these kind of signals. For a specific analysis, for a specific part of analysis, you can use this. So filters are having many application. It totally depends how you are going to use that in different application. I hope I am clear here about how you will design your filter using optimization. Any questions? So in my slide, I show you optimization through PSO only, but you can use many other optimization there. And you can also create your own objective function. You can make it constraint optimization by giving some constraint on a passband ripple, stop band ripple, or anything you can specify there. You can also go for multi-band filter, where you can specify the different band specification, and accordingly you can compute the magnitude response and then compare, depending on how you construct your objective function. Any questions? Okay, ideal is infinite. I think this has already answered during the time. Yes. Shefali, Hn is equal to H of mine, that is the even. Fine. And ideal is not infinite duration, that IAR filter is a infinite duration sequence. No, frequency response, yeah, you can say, but in that slide I was talking about the length of the sequence. If you have given the input as your impulses and then you compute output of it, the response, so the samples will be of finite duration, like 100 and 200, so it is having some finite value. I think rest is all answered. Okay, thank you everyone. I think our next expert is also joined.